be Tuesday afternoon? 2/3 of the way done. That means we're in the final stretch. We see the light at the end of the tunnel. Now the question is it an oncoming train? Or is it the exit? We introduce integration next. We don't study it too much this semester. All we do this semester is define what the integral is, look at the fundamental thing of calculus, so that allows us to evaluate integrals, and look at one technique. So the integral comes about from the area problem. Right, just like derivatives came from what's known as the velocity problem. So the area problem involves finding the area under a positive curve and above the positive x-axis. And the idea is we approximate this using rectangles. Which means we're going to be doing some summing. So we start by looking at properties of summation. So consider two sequences of terms. Call them a sub I and b sub I. Let C be some constant. When was I doing this? Following properties hold for all positive integers n and integers m between 1 and n. So first, we're going to be introduced, unless you've already taken discrete math, to sigma notation. Which is just a way to represent a summation. This is the sigma notation for a summation. So that is read the sum from I equals 1 to n of C. So that's just C plus C plus C plus C plus C n times, which is n times C. So that one's fairly obvious. Oh, by the way, these are finite sums. You'll study infinite sums next semester in Calc 2. Summation I equals 1 to n of C a sub I. It's just C times the summation I equals 1 to n of a sub I. That's the distributive property of summation. Summation I equals 1 to n of a sub I plus or minus b sub I. Summation of a sub I plus or minus the summation of b sub I. The commutative and associative properties. Properties 2 and 3 taken together are called the linearity properties. So summation is what's known as linear. I wonder if there's a course where you study that. It's called linear algebra. Which I know for certain at least 3 of you have to take. Oh, 4 of you, that's right, your comp sci. You have to take it as well. Summation I equals 1 to n of a sub I. Summation I equals 1 to m of a sub I. Plus the summation I equals m plus 1 to n of a sub I. All 4 of those are pretty obvious. You may want to keep these handy. I believe there are 3 of them. Sum from I equals 1 to n of I. So you're summing up the first n natural numbers. N times n plus 1 over 2. That's extremely useful. I could thus ask you for the sum of the first 1,000 integers. 1,000 times 1,001 all over 2 is that sum. And so 500 times 1,001. Sum of the squares of the first n integers. N times n plus 1 times 2n plus 1 over 6. And the sum of the cubes for the first n integers. N squared times the quantity n plus 1 squared all over 4. partitions. Set of points. X0, x1, x2 up to xn. With A being x0, B being xn, and then they're sequential. And so x0 less than x1, less than x2, so on and so forth. This divides the closed interval A to B into n subintervals, called a partition of the interval. So the partition is your set of points P. Notice what is not stated. How to pick your partition. Because you can pick it however you want.
Oh, can you give an example of what a difference between two partitions would look like?
So consider the interval 0 to 1.
Okay.
I want 3 subintervals. So my partition could be, how do I want to divide it? 1/3 and 2/3. Right, then you'd have 0 to 1/3, 1/3 to 2/3, and 2/3 to 1. I could also do 0.1 and 0.9. Or 0.2 and 0.3. I just have to choose any 2 points from 0 to 1.
Okay.
There is a special type of partition, one which you choose where each subinterval has the same length. This is called regular. Left endpoint approximation for area. On each subinterval, construct a rectangle with width delta x and height equal to f of x sub I minus 1. Right, so you use your left endpoint of the subinterval to determine the height of the rectangle. Area of this rectangle, f of x sub I minus 1 times delta x. If you add up all those areas, we get an approximation for the total area. This is known as the left endpoint approximation, and we typically denote it with L sub n. What's not stated is that the delta x is the same for each rectangle, so it is a regular partition.
Would there be any difference if this specific point on the graph was above or below the x-axis?
If the function?
Yeah.
This is for positive functions.
Okay, positive.
Although I guess theoretically it wouldn't matter. You just have a negative area, the signed area to represent whether it's above or below.
Okay.
So the only important thing is that formula. The rest you can write down later. And graphically, this is what we're doing. Oh, good. I brought back some nightmares. You had Calc 1 already? Oh, good. Does Riemann sum sound familiar? Good. This class is going to be more fun than I thought.
So if that does drop below the x-axis, that's negative area, which is subtract from the total area.
So the area itself isn't negative. We call it negative to represent that it's lying below
Okay.
the x-axis.
Right.
Well, we have a left endpoint approximation. Where there's a left, there must also be a right. Same idea, except this time we use the right endpoints to determine the height of the rectangle instead of the left endpoint. And then sum it up. And obviously for right endpoint, we use R sub n. Right, and then graphically, this is what's happening. Sorry. Oops. I'm going to go back there real quick. I'm going to look something up. Because either it's not in your book or I just flat out missed it. But there is a third approximation. Wow, it's really not in here. That's annoying. They said there is a third approximation that for some reason not in the book. There's technically an infinite number of approximations, but there's a third one that's commonly used.
Can we just take the height at any point in between the two endpoints?
You can.
All right, so I'm guessing sidewalk was the middle.
Midpoint, yeah, that's the third approximation. The midpoint approximation.
Midpoint formula then.
I'll introduce that when I need to.
So for the formula, would that just be a capital M on? No.
It's a little wonky. It technically would be xi minus 1, f of xi minus 1 plus xi all over 2.
Right.
But there's ways to do that where it involves your the left endpoint A. I'll introduce those as I need to.
So there's a better way.
Riemann sums. Yes. Named after the mathematician Bernard Riemann, who also has some findings in electricity and magnetism. I think specifically electricity. Let f of x be defined on a closed interval AB. Let P be a regular partition. Actually, it doesn't have to be regular. But for our purposes, I'm going to say it's regular. Let delta x be the width of each subinterval. Let x sub I star be any point in the subinterval xi minus 1 to xi. The Riemann sum is defined as the summation x equals I equals 1 to n f of x sub I star times delta x. Or if your partition doesn't have to be regular, partition. This would be the Riemann sum if you don't restrict it to being a regular partition. Right? It's the same formula, except now your delta x is not constant. Right? Your delta x depends on the subinterval. And you may see that notation, R of FCP means Riemann sum given the function f, collection of sample points C, and partition P.
Sorry, what were those three?
F is your function, C is the sample points, so it's the set of all your sample points,
Okay.
P is your partition.
Got it. Thank you.
So we've been approximating area. So I'm just going to go back to here real quick. As you can see, in this example, that'd be an overestimate of the area, right? How could you improve the accuracy?
Smaller subintervals.
Which means increasing the number of rectangles you have. How many rectangles do you think we would need to get the exact area?
Infinitely many.
Yep. If you're using regular partitions, n would represent the number of rectangles you have, the number of subintervals, then the total area would be the limit as n goes to infinity of your Riemann sum.
Do we have to use a Riemann sum for this?
That's always a Riemann sum, yes.
All right.
But all of the methods we've studied are Riemann sums, right? Left endpoint and right endpoint are both Riemann sums.
Oh, okay. So it's okay. I get it.
Now go back to what I wrote earlier, collection of sample points. Left endpoint would just be the left endpoint of each subinterval. That'd be your C. Right endpoint would be your right endpoint of each subinterval. So it still satisfies the definition. That is if the partition is regular. See if this notation looks familiar. Do you recognize that? Oh, that's a shame. Then you didn't study Riemann sums that well then. That notation, magnitude delta, is defined as the width of your longest subinterval. So if you let that width go to 0, then all of your subintervals are going to 0. The width of each subinterval is going to go to 0, which means your n goes to infinity. Right, but that would be the notation if your partition is not regular. But it means the exact same thing. Just a bigger pain to calculate. double absolute values of delta.
Right.
And it's just representing the width of the largest subinterval. I think it's just called the norm of the partition. Well, judging by that, areas are a bit of a pain to find. This leads us to the Riemann integral. And I call it Riemann integral because it's not the only integral. There's at least one other integral that I know of in math, and that's the Lebesgue integral. Which is just, you think the Riemann integral is bad to find? Lebesgue is worse. It's also more accurate. The Riemann integral, just called the integral, of f from a to b. I feel like standing up. It's represented by that.
And that's easier.
No, that's the integral. This isn't the Lebesgue integral. This is the Riemann integral.
Okay.
Right, so that's read the integral from a to b of f of x dx. Right, so that dx is very important. The differential for x, it's telling you what you're integrating with respect to. And it is the limit as n approaches infinity of the summation from I equals 1 to n, f of xi star delta x, provided that limit exists. Oh. So the integral is just the limit of a Riemann sum. And it doesn't matter what Riemann sum. There's a result that I don't cover that states that no matter how you form your Riemann sum, that limit is always the same.
Permission to only use the endpoint approximations.
That's typically what we use, the right endpoint,
Okay.
generally speaking. You can't do that for every function, though.
Like not possible or not allowed for this class?
Not possible. No, I don't want to say not possible. It makes the math impossible to do,
Okay.
to do it by hand. But we're not going to encounter that in this course. That is, doing functions like that is really going to be advanced. If the limit exists, we say that the function is integrable on a to b, or it is an integrable function. If f is continuous on an interval, it is also integrable on that interval. Every continuous function has an integral.
Does that mean every non-continuous function doesn't have one?
No.
Okay.
If it's discontinuous, it may or it may not be integrable. Well, that means that if f is positive, then the Riemann integral is just the area between the curve and the x-axis. What if f is not positive? Well, then it's just a signed area. So the integral actually represents a signed area between the curve of f and the x-axis. If f is totally positive over your interval, then you're going to have a positive signed area. If it's totally negative, it's a negative signed area. And if it's both, so you have positive and negative. Positive signed area would mean you have more area above the x-axis than below. Negative signed area would mean you have more area located below than above. And a signed area of 0 means you have equal area between both above and below. Right, so it's the same notion as displacement. You start at home, come to class, you go back home. What's your displacement?
0.
0. That is different than distance. Signed area is different than area. If you want the area, the total area, then it's the integral of the absolute value of the function. So some properties. Integral a to a is always 0. That makes sense. Point. Well, there's nothing under a point, right? There's no area. The area is 0. I guess you could argue it's a line, but that still means that the area of a line is 0. This one is important and often forgotten. The integral from a to b is negative integral from b to a. You can change your order of integration by multiplying by -1. Which means there is no rule that says your lower limit of integration has to be the smaller value. That is also an important concept, especially when you move on to applications of integration, specifically in physics. Integral of a sum or difference is the sum of the integrals. Integral of a constant multiple is the constant multiple of the integral. So the integral is linear, which makes sense because it's just limit of a sum, and both limits and sums are linear. c is any number in the interval a to b, then the integral from a to b is the integral a to c plus the integral c to b. So you can split your integral. That is, again, another useful property and something you want to keep in mind. And finally, you have a comparison theorem. I believe there's 3 of them. There's 3 parts to it. If f of x is greater than or equal to 0 for x between a and b, then your integral is going to be greater than or equal to 0. So a non-negative function results in a non-negative integral. If you think about it geometrically, that makes sense. Right? If your function is non-negative, then your signed area has got to be non-negative. If f of x is greater than or equal to g of x over the interval a to b, then your integral of f is greater than or equal to the integral of g. Again, think about it geometrically. That makes sense. And finally, you have 2 constants, little m and big M, that serve as bounds for the values of f. Little m is your lower bound, capital M is your upper bound. Then, little m times b minus a, little m times the length of your interval, is less than or equal to the integral, which is less than or equal to capital M times the length. Some quick comments. Recall the definition of the derivative, the limit definition, versus the limit definition of the integral. Which one is algebraically easier? F of x plus h minus f of x over h, or a sum that you need to find the limit of?
I think it depends on the f of x.
It's always the derivative.
Always derivative, that's always easier.
Algebraically, that's always going to be simpler. I said algebraically. This means, generally speaking, derivatives are probably 10 times easier to calculate than integrals. Integrals are very difficult. That's why you spend half of Calc 2 doing them. Also, I haven't studied antiderivatives yet, but we will. Generally speaking, just about every single function has a derivative function. Right? If I give you any function f of x, you can find its derivative. The same can't be said for integration.
Not every continuous function would have an interval.
They do. However, only less than 1% of the functions can be analytically found. meaning the other 99+% of the functions you have to do numerical techniques on. Which means coding. And it's only ever an approximation to the true integral. Integrals suck. Sadly, integrals are also extremely useful. Now, just like we did with derivatives, we're going to start the painful way by calculating integrals using the limit definition. Then we'll look at the shortcut. So we want to evaluate R6 for the function sine of x over the interval 0 to pi. So remember, R6 means right endpoint approximation with 6 subintervals. So what should the length of each subinterval be? Remember, right endpoint is regular. Start with that. How long? What's the width of each subinterval?
Only pi long, so pi over 6.
Yes. I will list out each subinterval.
Are we finding the area or assigned area?
No, just R6,
Just R6.
which is an approximation for area.
All right.
And in this case, it doesn't matter because sine of x is positive over 0 to pi.
Right.
6 subintervals as desired.
So we're just adding all those together now.
But remember, delta x is constant. So we can pull the delta x out of the summation. Pi over 6 times right endpoint of your first subinterval is what? was the right endpoint of the first subinterval?
I over 6.
That's your I equals 1 term. Right endpoint of the second is pi over 3. Of the third is pi over 2. Of the fourth is 2 pi over 3. Then pi over 6. And finally, of pi. Sine of pi over 6 is what?
1/2.
What about pi over 3?
Square root of 3 over 2.
Pi over 2?
That's 1.
2 pi over 3?
So, I think that's still square root of 3 over 3.
5 pi over 6?
1/2.
Pi.
0.
Half plus half is 1. Root 3 over 2 plus root 3 over 2 is root 3. So that's what? 2 plus root 3?
Yeah.
Times pi over 6. That's the exact value of R6. Which serves as an approximation for the area. L5 of 2 to the x over 0 to 3. L5 represents left endpoint 5 subintervals. And they're regular. So what is delta x? Again, I will list out the subintervals. So again, it's actually probably correct. So I can just make that x sub I for the right endpoint. Left endpoint's f of xi minus 1. Right, using the left endpoint for each subinterval. Left endpoint for the first subinterval.
That's 0.
Second.
3 over 5.
Third.
6 over 5.
Fourth.
9 over 5.
And fifth.
12 over 5.
Only one of those has a nice value. That's 2 to the 0. That would be your exact value. I mean, L5 is already an approximation, so we might as well just approximate it.
All right.
Let's go to, I don't know, L5, 5 decimal places.
Okay.
So evaluate that to 5 decimal places.
I have a value behind it.
What'd you get?
I got approximately 8.14401.
So again, that serves as an approximate area. It's not a good approximate, by the way. It's still an approximate.
I think there's better approximate 20 subdivisions.
20?
20,
20 subintervals?
better than 5.
Better than 5, but still not good.
200.
That would probably be good. To be fair. 20,000 would be good. You'll determine how to find how many subintervals for desired accuracy in numerical analysis. Calc 2, you'll learn how to code to do this. I guess it depends on who you have. If you have me, you'll be learning how to code. Or if you have Ilje Ilajasu, she also does coding. You'll learn how to code. You're going to have to learn how to code eventually as an engineer. Might as well learn now while it's simple. Yeah, well, too bad, because in engineering they make you use MATLAB, which is awful. It's probably the worst language I've ever used. I hate it with a passion. Switch to physics. It's better. Ah, M3. What do you think the M stands for? Midpoint.
Midpoint.
Same rule. M is regular. So each delta x is going to be the same. And you're going to choose the midpoint of each subinterval as your sample point. So what's delta x?
One of
So those are the three subintervals. Remember, midpoint of 2 points is just the average. Midpoint of 1 4/3. What about 4/3 and 5/3? 5/3 and 2. 11 what? We can simplify that if we so desired. You have the sum of logs, it's the log of the product. So it'd be log of 7 times 9 times 11 all over 6 cubed. 6 cubed, I believe, is 216. Yeah, 36 times 6, 216.
Yep.
7 times 9 times 11, yeah, damn that. That's what, 63 times 11? Well, that's not too bad. 63 times 10 is 630. 630 plus 63, 693.
I also checked it correctly.
Let's go to 3 decimal places. What is that? As an approximate area. Okay. Those were just a given value of n. Now we're going to let n go to infinity, and we'll do that. What's that? Thursday? No, Tuesday. Today's Tuesday. That we'll do on Thursday. So we're actually going to be working with Riemann sums and limits of Riemann sums on Thursday. So let's see. Looks like you only have one assignment.